And the second is that we have partnered for this event with Latvian Investment Development Agency. And we welcomed the best Latvian startups in the area of artificial intelligence. So here, next door, we have a startup launch with representatives of startups such as Lovat, Asia, Octomax, Avocado, SizeRadar, Marine Digital, and Samsab. And you will hear from those startups more. And now to the beginning of the conference. And as I told, we handpicked all the key speakers. And I personally have discussed every presentation and with every speaker in this conference. Our first keynote speaker, Ivan Yamshchikov, is a very rare breed. He combines in himself a serious scientist who works for Institute for AI and Cognition in Max Planck Institute for the mathematics and science. And he also works for ABBYY as artificial intelligence evangelist. So he is a rare breed of scientists who, like Feynman and Kintai-Garoski, capable of digesting science into simple and entertaining language. So I'm very much welcome Ivan Yamshchikov to the scene. Ivan.
Thank you very much. You're too kind. Comparison with Feynman is kind of flattering, but thanks a lot for being here. It's great that such companies as Deloitte and Visa are looking at the startups as well. I think it deserves a shout out that there is understanding that innovation is something that moves us all forward. So yeah, I'll talk about the AI, and starting from the opening today, like 5 minutes ago, there are two ideas that I completely disagree with. One is that there is a fight between AI and humans. It sounds to me like there is a fight between humans and hammers, you know. And I'll try to explain why Terminator 2 is a great movie, but it doesn't have anything to do with us. And two, there was this statement, nobody understands how AI works. And we'll also try to dig into that and try to explain that there's, well, it's relatively understandable, let's put it this way. Okay, so why should you listen to me? Well, Igor put it quite well. I have experience from three sides. So first of all, I do research actively in Max Planck Institute in Leipzig in Germany. I have a PhD in financial mathematics, so I understand what are the pains of financial industry, and I understand how much data financial industry has. And I'm frankly very surprised that in terms of driving the innovation so far, it's mostly internet-based companies that are driving these frameworks at the moment. But I really hope that financial industry can catch up because it's got enormous resources and incredible talent, and I know it firsthand. And I also work for ABBYY. We do document processing and process analytics worldwide. So I understand the business perspective as well. And I have a side project called Creaited Labs where we do generative AI and creative AI. So we try to do the things that machine cannot do, right? So whenever we hear machine cannot do this or machine cannot do that, we try to make it a problem and try to solve it. This is what I do. And if you're interested in the papers, you can go with the QR code and check them out. But I try to give you an overview of what artificial intelligence is from very different perspectives. And we'll talk about some history. We'll talk about the thing that people call data clips. That happens right now. It is happening at the moment as we sit here. Then we'll do some overview of methods and applications that people currently use, that currently work in business. And then we'll also talk about challenges and bottlenecks, because it's not very rosy all the time. Implementing AI is hard work. If you try to implement some artificial intelligence or some machine learning algorithm, you probably know that. But first, let's discuss the terms, okay? Because terms are very important. Because AI is such a hypey topic that it's very important to understand what we talk about, right? So, what is artificial intelligence? Well, as a scientist, I don't know. Not because it's something tricky or complicated, but because journalists call everything artificial intelligence now. Every second publication about anything is about artificial intelligence. So my suggestion is you call a system artificial intelligence if it is cleverer than an average journalist, okay? This is the definition. If it performs something that average journalist doesn't understand, it's artificial intelligence. However, within this artificial intelligence, there are two concepts. There's weak AI and strong AI. And weak AI, scientists usually talk about it when we talk about specific problem that is very well defined, very well measured, that we want to improve or solve, okay? And within this weak AI area, there is this machine learning thing. So machine learning is a lot of different algorithms that are basically derived from the laziness of the humans, you know? Humans don't like to work with clanky big data sheets. And especially when these data sheets becomes enormous, then they want algorithms to work with them. And there are three big branches. There is unsupervised learning, when we deal with unstructured or semi-structured data. There is supervised learning, when we have ground truth. We have labels that tell us what is right and what is wrong, and these labels are human provided. And finally, there's reinforcement learning. Raise your hand if you have a dog. Do you have a dog? Good. So each person who has a dog knows what is reinforcement learning. Okay? Reinforcement learning is when you work as environment and you reinforce your algorithm with food or saying good dog if something good happens, because you want this behavior to continue happening. And we can do the same with algorithms. For example, famous algorithm AlphaGo by Google that was playing a Go better than world champion was trained exactly this way. But for algorithms, you don't need to give them food. You just give them +1 and then they are happy. Okay? So it's a bit easier to do reinforcement learning with algorithm than with a dog. And what you should remember about weak AI is that despite that it is weak, which means it's very well defined on a narrow task, it actually works. But there is this strong AI, which is very scary. And the funny thing is the word robot and the concept of a scary robot come from the same place. It was a Czech fantasy book writer, Karl Čapek, and he came up with the word robots in 1923. And in this first novel where robots were mentioned, these robots go rogue and kill all humans and everything like that. And then they understand that they cannot reproduce, they fall in love and become new Adam and Eve for a new and better humanity. So this narrative of good robots and bad robots is 100 years old. Forget about it. People didn't know anything about robots back then. So the thing we should understand about strong AI, which is the AI that's general and can do whatever it wants, is that it doesn't work. It doesn't exist, we don't know when it's going to happen, and we don't know how to build it. And the paradigm of like people versus robots is a very strange paradigm, because we know so many areas where technology helps us to do better that it's so weird that we're still afraid of it. So now let's discuss a bit of a history. How old do you think the machine learning area of expertise is? How long do scientists work on it? Who think it's like 20 years old? Raise your hands. 30, 40, 50, 100. Okay, quite well. Well, technically, this wave of AI is not something very new. It's happening with us for at least 70 years. At least. So if you're somewhere between like 40 and 100, you're actually quite well. Because this is 150, this is when Alan Turing comes up with the idea of Turing test. Turing test is this idea that if you send messages to the robot and the robot answers, so you cannot distinguish if this is the human who is answering or a robot, it means that you created a general artificial intelligence. Well, two interesting points. One, this concept is a philosophy paper. It's published in the journal Mind by Royal Philosopher Society, and it is the most quoted philosophy paper in this journal, so philosophers probably are biting their elbows that computer scientists did it. The second thing is that we're 70 years into the history, and we still don't even come close to this idea on how to create machines like this. There are challenges to compete with Turing tests, but we still don't quite understand how to make a robot that rationalizes. And then there is a huge wave of different major achievements of this research. There are several AI winters. And one of the big problems with AI winters, of course, is that as it happens, people start to expect a lot from the technologies, and mostly these are the people who don't know how the technology work, and they overheat the whole area. And this is something that's happening right now. So I strongly encourage you, later today we'll also talk about the bottlenecks. So don't overheat it. It's very useful, but don't expect it to do anything. It can do a lot, but not everything. Another very interesting milestone is over here. So 1982, a lot of brilliant people start to say, hey, artificial neural networks is an interesting type of algorithm, okay? And for the next 40 years, they keep on saying that, and people who listen to them say, well, it's nice, but it doesn't work. So what is funny is that the first laureates of Turing Prize, Joshua Benio, Jan LeCun, and Geoffrey Hinton, they came up with the methods of artificial neural networks training in the 80s. And then for 30 years, at least, people were joking that an artificial neural network is the second best thing to solve any problem. Because these algorithms were very generic, but they couldn't achieve the performance that specific algorithms designed for one specific problem were achieving. And only in 30 years, when we got enough computational power and enough data, we found out that these algorithms actually work. And the first Turing Prize, which is the analog of Nobel Prize, but for computer scientists, the first Turing Prize was given to the people who were saying that the things will work for 30 years in a row. Joshua Benio, Jan LeCun, and Geoffrey Hinton, 2 years ago. So it's a very long process. When people tell you that AI revolution happened yesterday, they probably don't know anything about AI and revolutions. Revolutions take a long time to happen. This is very important. Okay, so let's move on. Yeah, this is the slide that I love. So this is the estimation of the IDC. And this is the estimated amount of globally available data that is available to businesses for analysis. In 2013, 2018, and 2025, this is the estimate. Who knows what is a zettabyte? You do, great. It's very rare. You are super smart. You shouldn't be here. You will not learn anything from my talk. Go have a coffee. But, okay, so zettabyte is 10 to the power of 12 gigabytes. You probably know what is gigabyte, right? Probably you remember when Steve Jobs was presenting the first iPod, he was saying, gigabyte is 1,000 songs. So this is where we want to be with 1 gigabyte, okay? And you take gigabyte, you multiply it with 1 and 12 zeros, and you get 1 zettabyte. Now, what is 1 with 12 zeros? This is also something you probably don't think about too much. If I take the length of my elbow and multiply it with 1 with 12 zeros, this will be the distance from here to the sun. Okay? And we had 4 of this back in 2013, and we're gonna have 175 in 2025. So data clips is something that's actually happening, and we have to use technology to do something about it. We don't have a chance to do anything, we cannot, there is no workaround. We don't have that amount of people, and the people probably would not do this work because it's incredibly boring. So this is why we need to address this issue. Now, how do we address it? Well, there is a lot of different algorithms within machine learning, and I partly covered that there are 3 principal tasks, and there are a lot of different algorithms that could be used to perform these tasks. But probably, again, the most hypey type of algorithm is artificial neural network. And in order to demystify it, we will now try to understand how it works so that you know that it's not as mystical as you think. Okay, so you will now be an artificial neural network, okay? So each of you would perform as an individual neuron. What does individual neuron do? Well, originally, when people came up with this idea, well, first of all, you need to understand, nobody is as arrogant as mathematicians. Okay? So when we learned something about brain in the 50s, people were like, ha, that's easy. Brain works like this. There is a cell, there is a connection to another cell. We can just reproduce this in silico. And they had this very simple individual elements that performed very simple tasks, and they connected them to different elements. and they had inputs and outputs, and they said, we will change the weights of these connections, and this is how these things would learn. And then it took them 70 years to understand how to actually do it. But this is how it works now. So let's say you all are layers of the network, okay? So you as a person, now you're a neuron, and you behave in the following way. If you sit in the first row, I'll tell you what to do. You don't need to worry. You will be the first layer that's called initialization layer, or input layer. And if you sit on the second row or further, your rule is very simple. Choose people in front of you, on the row in front of you. Choose 5 people. And if 2 of them raise their hands, 2 or more, you raise your hand as well, okay? Everybody understood the rules? So if you look at people in the row in front of you, if 2 of them raise their hands, you raise your hand too, okay? You people, you will also count as the first row, despite the fact that you sit on the second one. Okay, good. And the gentleman over there, somewhere, yeah, I think the gentleman that sits in the very last row on the sofa. Can you hear me? Yes, wonderful. You will be our output neuron. So you will look at everybody in the last row, and if majority of them raise their hands, you also raise your hand, okay? Great. Okay, and the first row, raise your hands now. Let's say if you were born in summer or in autumn. Raise your hands. Second row, third row, fourth row, fifth. Look at the people in front of you. And if the majority of them raise their hands, raise your hand. Yeah, yeah, yeah. Output neuron, how does it look? No, no signal. Good. This is good. This is one iteration of a convolutional network going one way. And the output neuron, it could be many, it could be one, but this is the output layer. Let's say we want to train a classifier to classify images of, dogs from cats. Yeah? And the first input layer was behaving this way not because you were born in a certain period of time, but because you saw certain configuration of pixels on the picture that made you activate. And let's say if there is 0 on the output, it means that it is a picture of a cat, and if it's 1 on the output, it means it's a picture of a dog. And let's say we show the picture of a cat, right? So there is 0, it's a correct answer. So what happens now is I tell to this last neuron, I say, we did a very good job. Good job. It was correct answer. So the last neuron tells to the neurons in the pre-last layer, to the neurons that this neuron was looking at, says, hey guys, we did a good job. And he starts to trust neurons that didn't raise their hand a bit more, and start to trust neurons that raise their hands a bit less, okay? And then the next layer tells that to the pre-last layer, and so on, and so on, and so on, until we reach the first layer. So after the first iteration, this thing is called backpropagation. This is how we learn artificial neural networks. And after the one cycle, you now look at the same people you were looking before, but you trust some people more and you trust some people less. Yeah? So now if you see that one person raised their hand, and it is a very trustworthy person, and everybody else didn't, you still probably would raise your hand, okay? And we do it millions of times. And then, surprisingly, we can classify cats from dogs, okay? So it's not very mysterious. I mean, it's difficult. It's very hard to understand how people came up with this thing, but it works, and it's kind of straightforward, okay? Please, please, keep this idea in mind. It's very important. Okay, let's move on. How can we use these things? Well, you need to understand that I explained you one type of certain artificial neural network. There are plenty of other algorithms, but what is important to know is that they work like Lego, okay? So once you understand certain algorithms, you can stack them on top of each other, you can combine them, and you get new and new solutions. So this is one of the examples that we had in ABBYY. We do optical character recognition, and well, with many languages it's a bit hard, especially hard with Chinese, because you need to recognize 30,000 different pictures, right? So what we do at the moment, this is our state-of-the-art solution, is that we have first classifier that groups pictograms in the classes. So these are outputs of the first initial convolutional neural network. And if you don't speak Chinese, and I don't, and you look at these pictures in every row, they look very similar, right? And then for each group, we have a separate neural network that is trained to recognize this particular group, okay? So this is an example of this Lego technology, when you have the first like rough classification, and then a more precise and minute one that works with every group. And actually, this stacking of technology happens all over in various contexts and examples. This is something that you just need to understand, that no matter how complicated the final solution is, it consists of these Lego blocks of algorithms, okay? Good. Now, the next thing I want you to understand is that these technologies could be applied to anything. And one of my favorite examples is this startup called Kettle Care. It's an actual startup that uses artificial intelligence to improve cow farming, okay? So it turns out that in order to have more milk, for example, you want your cows to have less stress. And if your farmer forgot the cow in the headlock, the cow has stress and gives less milk, okay? So you open the headlock because your machine vision notifies you that, hey, there is a problem. And it also turns out that you can actually recognize individual cow by the colors of its back. So literally, once you have enough data for almost any well-posed task that weak AI is capable of, you can improve it and automatize it and make it better, even if it's about cow milking, okay? Good. Now let's talk about possible bottlenecks. Whenever you talk to, there are two types of data scientists, okay? One type of data scientist is the person who is very happy, and this probably means that this person doesn't code, okay? You talk to this person, and the person is like, for sure, we can do it. It's no problem. 3 weeks, just give us the data, we'll do it. It's very easy. And then there's this sad person that doesn't speak that much, and you talk to this person, and this person is like, I don't know. This is a very standard answer. And the reason is because whenever you pose a problem for weak AI, so well-posed problem, you think that the problem looks like this. You want to classify the beans, coffee beans, and you want to see the roasted beans in one group and the unroasted beans in the other group, right? And this is how the problem looks for the person who doesn't try to solve it. Once you start to work with actual data, you understand that every problem looks like this. And there is a lot of nuance and a lot of deliberation. And as you implement the systems, you kind of need to have a cutoff, right? You need to choose which bean is not roasted and which one is, right? And this decision at the moment is either made by a human consciously or is made by the algorithm because human forgot to make this decision, okay? And this brings a lot of interesting bottlenecks and challenges. And there is one very good example. So there's a very well-known story that an underage teenager got pregnant and Target knew about it earlier than her father, right? Well, it turns out to be a scoop. It's not completely true, but it's actually feasible. Nowadays, if you know the consumer preferences of your client, you can predict pregnancy better than relatives. And you probably don't want to do that. But you have to think about it in advance while you implement the solution. This is one of the big challenges that we have to think, and it's, I think, more important than war between robots and people, is how we deliberate and how we make decisions about what information we want to use and what information we don't want to use in our solutions, okay? Now, I'll give you some other examples that are less scoopy and actually scientific papers. So this one I really like. It's called Predicting History. These both examples are from this broad area of digital history, when people try to use data from social networks and some other available data to kind of quantitatively describe historical processes. So here what they did is that they used the data from the Ministry of Foreign Affairs, Foreign Office in the US, and they used the notes that diplomats sent to the ministry, to the Foreign Office, about certain events. And they said, hey, can we train AI to predict if event is historic or not? Okay? And it turns out that if you have 50% of historic events and 50% of some random non-historic ones, you can predict it like with almost 100% accuracy. Your algorithm works really well. You can predict historic events. But in reality, there is a very small amount of historic events and a lot of events that are useless. And if you have actual data and train the algorithm on actual data, then predictive power of the model is 0. Okay? So for your businesses, it basically transfers to a very simple idea. If you work with very rare events, and then you formulate the training data set in a way that you balance rare events with some events that are not rare, that happen quite often, and you make it balanced because you hope to get some signal out of it. Yeah? For example, you send cars, you send Range Rovers. And if you sell Range Rovers, you don't have a lot of sales, right? So it's useless to train your data on this biased data set where the world looks like 50% of the time I sell the Range Rover, you know? You have to train your algorithms on actual data, and quite often they turn to be incapable of giving you a solution. This is very important to keep in mind. Another example that I really like is the example of how English-speaking Israeli and Palestinian media are naming the border between Israel and Palestine. English-speaking Israeli media call it security fence, and Palestinian affiliated media call it apartheid wall. And it's the same border. What is more interesting is that if you Google security fence, you get one type of imagery. But if you Google apartheid wall, you get another type of imagery. And it's the same border. This is a very good example how humanly projected biases are acquired by the algorithms, okay? So you see what happens here. There is a political discourse that two sides try to enforce on the public, and there's the algorithm that starts to think that security fence and apartheid wall are two different entities, okay? And you need to remember about it once you do your implementations. Now, finally, let's talk about the challenges. So this is the data of US Bureau of Labor Statistics. 60% of occupations, approximately 30% of activity in them could be automated in the nearest future. And by 2020, Gartner predicts that 40% of business processes may be automated. And where is the money in this automation business? Well, it turns out that it's mostly in two things. It's either in predictable physical labor, which is robots, it always was there, but it's collection and processing of data. This is a huge part, 50% of all working hours is dealing with this area. Now, why I think that it's actually a good thing. So there is this beautiful picture by McKinsey, and here are different works, different occupations, and you have automobility percentage on one line, and you have the hourly wage on the other. And you have to see that this is the quantum. These jobs are going to be severely automated. And there is a file clerk over here, and there is a landscaping worker. They get approximately the comparable hourly wage. But if we talk, and if we make a bet, who is happier? My money is on the landscape worker. So as long as we stay humane, democratic, and rational, I think this is a huge potential that we can harness to make people happier on average. Now, finally, two last things that I want you to take out of this talk, and I'll be done. One thing is that future is measurable. So if you don't measure something about your business, ask yourself why. Because even if it's the cow milking business, it turns out that you can improve it as long as you start measuring it, okay? And you run financial businesses, you run e-commerce, you have a lot of data naturally. Think about whether you measure it, whether you gather it, and how can you harness it in the future. And the second thing is my favorite slide ever. So look at these two chairs, and in your head, think when was the first chair designed and when was the second chair designed. Let's say, in which decade? They both were designed in the 20th century. So let's say 10th, 20s, 30s, 40s, 50s, 60s, 70s, 80s, or 90s. Think in your head, make a decision. What would be approximately the year for this one, and what would be for this one? Are ready, everybody? Good. So they actually designed in the same year, 1929. But this one is designed by the Bauhaus designer, and this one is designed by the Art Deco era that was already kind of wrapping up. So what was the big thing about Bauhaus? They said, we know that plastics, glass, and metal are very expensive now, but they will be cheaper in future. Let's design things as if we have these technologies available and cheap already. And this is basically how they invented 20th century. All the things around us are inspired by these people, by Bauhaus people, because they thought, let's think about this technology as if we already have it available and cheap. And this is how I encourage you to think about AI. Once the technology is available, it will only get more and more widespread and more affordable for people. And if you think about your businesses in terms of this elastic future, you might come up with something that in several decades would still look very modern. And if you don't, you might come up with something, well, that I don't want to sit on, right? Thank you very much. This is all I have. Thank you for your attention. And if you have... Do we have time for one last question, or I don't know? If we do...
Yes, I think we have time for one question.
Okay, there is one over there. Do we have a mic? No? Yeah, if you speak Russian, tune into my podcast. We also talk there about technology, but it's not available in English. I'm sorry.
Hi.
Hello.
I'm Dmitry. Thank you for the presentation. You mentioned that the strong AI is close to impossible, or very hard to make.
I didn't say impossible. I said that it doesn't work, and we don't know if it is possible.
Yeah. Okay. And you also mentioned the weak AIs that work for specific tasks. Yeah. And we also can combine weak AIs to provide more complex tasks.
Sure.
And now, when we have a critical mass of weak AIs in various fields, if they get connected together, and there will be maybe AI that knows how to connect them together, will we get a strong AI or not? Thank you.
I think this is, first of all, this is very speculative, and because again, this is a hypothesized thing. And second thing is, of course, when we talk about AGI or artificial general intelligence or strong intelligence, we usually think about deliberation, right? We usually think about the possibility of an algorithm to make certain decisions on its own. So a combination of weak AIs that is huge enough to perform a lot of different data lacks fundamental motivation to do that, right? So I think when we talk about general intelligence, we expect the algorithm to kind of make tasks for itself and then solve them. And combination, no matter how sophisticated is your combination of weak AIs, this doesn't happen, okay? And this is actually the huge bottleneck, because we don't know what is the nature of willpower and what is the nature of deliberation. And there are a lot of very fringe theories about it. For example, Sir Roger Penrose thinks that the deliberation and consciousness are quantum, and he has the whole theory about it in this book, New Veil of the King's New Veil, right? But it's very, very far-fetched. We don't understand how will and deliberation works, and this is what distinguishes weak AI from the strong AI. Okay? Good. Thank you very much.
Thank you, Ivan.